So the next concept that I want to cover here is aqueous solutions. And so when you dissolve a solid in water, like salt or sugar, what you have is an aqueous solution. Solution, by definition, is basically a homogeneous mixture. So you can have a liquid solution, you can have a solid solution, you can have a gas solution. So it's essentially a homogeneous mixture. But more specifically, I want to talk about aqueous solution here. Basically, you have solids like sodium salt or sodium chloride salt, or any ionic compounds, or maybe even sugar that's dissolved in water. Hence, we have aqueous solution. So a lot of chemical reactions actually happen in water. And so it's important that we talk about what's actually happening when solids like salts and sugar dissolve in water. So when you dissolve a salt like sodium chloride in water, what you have is a salt solution, specifically sodium chloride solution, because there are other salts out there like potassium bromide, for example, or sodium iodide. So NaCl, or sodium chloride, dissolved in water is called a sodium chloride solution. If you have sugar dissolved in water, you have sugar solution, or maybe glucose solution. And these solutions, as I mentioned earlier, are examples of homogeneous mixture because they're all the components are blended uniformly together. And so a homogeneous mixture dissolved in liquid is known as a solution. And so in every solution you have two components. One is known as the solvent, and the second one is known as the solute. And the solvent is always the major component. For example, you can have solvent like water, you can have organic liquids or organic solvents. Organic meaning it contains carbons and hydrogens in their chemical formulas. Solute, on the other hand, is the minor component. So for example, when you dissolve sugar and salt in water, those are your solutes because they are the minor component. You have less amount of it compared to the solvent. And the term solvent is actually not just restricted to liquids. So you can use the term solvent in solids and in gases. So for example, if we're talking about air, when you look at the different components of air, you have nitrogen gas, oxygen gas, carbon dioxide gas, and small amounts of other gases like helium or argon. And so air, as you know, it's a homogeneous mixture because the different gases are blended uniformly, and you can't really tell the difference between the gases. And so it is a homogeneous mixture, and so it is a solution, an air solution or a gas solution. Okay, and so because nitrogen gas is the major component, which comprises of 70%, nitrogen gas is considered the solvent, and everything else would be considered solute because they are the minor components. But our main focus here is in aqueous solutions. Basically, you have solids that are dissolved completely in solvents or liquids. And so aqueous solution is basically a solution in which water is the liquid solvent. So because a solution contains a solvent and a solute, we can describe the amount of solute dissolved in a solvent using this concept known as concentration. Solution concentration. So we can describe solutions quantitatively as either dilute or concentrated. So when you have a dilute solution, that means that it's not very concentrated, that you have a small amount of solute dissolved in the solvent. Whereas a concentrated solution means that you have a large amount of solutes in relative to the amount of solvent. And so, for example, if you have black coffee, right, you brewed some coffee and you see that the coffee is black. So that means that it's very concentrated. And so if you take, let's say, a small amount of that coffee and then you added more water to it, then you're basically diluting that solution, meaning you're making it less concentrated. And so concentration is typically related to the color of the solution. So for example, a concentrated solution typically has a darker color. But then when you dilute that solution to a less concentration, the color changes to a lighter color. Okay, so you have a concentrated solution on the left and a less concentrated solution on the right, also known as a dilute solution. So there's a lot of different ways that you can describe concentration. But in this lecture, we're only going to cover one of them, which is molarity. So you have to remember what molarity is. That's the type of concentration. And this is one of the most common ways to express the concentration of a solution, a solute dissolved in a solvent. So molarity is, by definition, the amount of solute in moles divided by the volume of the solution in liters. So this is the total volume of the solution. So when it says volume of the solution, this includes the volume of your solvent plus the volume of the solute. Because remember that solutes, they do have volume because they take up space. Okay, that's what matter is defined as, right? Matter is defined as something that takes up space, which means volume, although at a lesser extent. So molarity has the symbol capital M. So M, or molarity, is equivalent to the amount of solute in moles divided by the total volume of the solution, meaning the solvent volume plus the volume of the solute. And this is in liters. So molarity is in moles per liter. So this amount of solute in moles can be calculated from the mass of the solute, usually in grams, and the molar mass of that solute. Okay, so molar mass is grams per mole, and the mass of solute is in grams. You can use those two information to calculate the number of moles of the solute. And so because of that, you can use this other equation that basically converts the mass in grams to number of moles. So you're basically dividing the mass of the solute in grams by the molar mass of that substance. And then you divide that entire thing by the volume of the solution. And so this numerator right here in moles is essentially the same or equivalent to this right here. Mass in grams divided by the molar mass gives you the number of moles. All right, so molarity is equal to mass in grams divided by the molar mass divided by the total volume of the solution. So if you're trying to get a bachelor's degree in chemistry or in biology, most universities require that you join a research lab for 2 semesters and that you perform research experiments in order to get your bachelor's degree. And so before you join a lab, typically they'll ask you a question, a mathematical question. Like, for example, do you know how to prepare a sodium chloride solution, for example, right? And then you're going to perform some mathematical calculation. So that's the first part. And then the second part is how you actually do it when you go to the lab. Okay, so unfortunately, you're taking an online course, and so I can't show you how to actually make it. And so I can only use graphics here, diagrams and figures and stuff like that, on how to prepare solutions, like sodium chloride solution. So this is how you'd prepare a 1 liter, 1 molar sodium chloride solution. So what you use is basically what they call a volumetric flask. So this is a volumetric flask shown right here. Okay, so this is a volumetric flask, and a volumetric flask is basically a very accurate glassware. It's a lot more accurate compared to a graduated cylinder or an Erlenmeyer flask or a beaker for that matter. Okay, so this is very expensive. And so what you do is you first calculate how much sodium chloride you will need to make this 1 liter 1 molar solution. And so I'll show you on one example in the next slide how to do the calculations. But the formula or the equation is basically the one I showed you earlier. So once you've calculated the mass of sodium chloride that you need, then you're going to pour this into the volumetric flask. So you're going to put this into the I keep saying graduated cylinder, volumetric flask, and then you add water. Not all the way to the top, but maybe half the volume right over here. And then you try to dissolve the sodium chloride pellets completely by shaking, and then you fill it up all the way to this mark right here. So this is typically the 1 liter mark, and this mark is etched on the glassware. All right, and then you shake it and you have your 1 molar sodium chloride solution. So molarity is the type of concentration, but once you've created the concentration, you can call it molar concentration or molar solution. So here's a mathematical example. What is the molarity of a solution containing 5.5 grams of potassium bromide, KBr, dissolved in enough water to make a volume total of 1.75 liter solution? All right, so whenever you're calculating concentration, which is molarity, you can use that equation that I gave you. Okay, you can use the second equation that I gave you earlier. So capital M for molarity is equivalent to mass of the solute in grams divided by the molar mass of that solute divided by the total volume of the solution. So notice that you're given the mass of the solute. So KBr is our solute, and this is the volume of the solution. So mass divided by the molar mass of KBr divided by 1.75 liters gives you the concentration of the solution. So the only thing that's missing here in this information is the molar mass of KBr, which is something that you can calculate using the periodic table. And so this is the equation, but a better equation to use is the second equation that I showed you. And so the first step is basically converting mass of the solute from grams to moles using the molar mass of KBr. And so we have 5.5 grams of KBr. Converting this to moles of KBr using the molar mass of the compound, grams would cancel, and you're left with the moles of KBr, so 0.0462 moles. And then once you've calculated the mole of KBr, you divide the volume of the solution, which is 1.75 liters. So 0.0462 divided by 1.75, that gives us 0.026 molar KBr solution. So you can use these steps, or you can just plug it in all the numbers into this equation that I showed you in the previous slides. So the total mass of KBr divided by the molar mass of KBr, which is 119, divided by the volume, which is 1.75. And that gives you the same number, 0.026 molar solution. Notice that this number is a small number, right? Because you have a bunch of zeros here, 0.026. So some researchers or scientists, they use the metric system, the prefix. Like, for example, you can turn this into millimolar solution. So all you have to do is move this decimal point 3 spaces to the right, and what you have is a millimolar solution. So that would be 26 millimolar KBr solution. Sometimes people even use micromolar solution. Since the units for molarity are moles per liter, which is a ratio, we can use this as a conversion factor. We can use this as a conversion factor whenever converting between moles of the solute and liters of the solution. So for example, if we have 0.5 molar solution of sodium chloride, we can turn this into a conversion factor, right? Because 0.5 molarity is basically 0.5 moles per liter. So this is equivalent to 0.5 mole of sodium chloride per 1 liter solution. Or we can do the inverse, which is 1 liter solution per 0.5 moles sodium chloride. So let's look at an example here and see how we can use this information. So let's say we have this scenario here. How many liters of a 0.125 molar sodium hydroxide solution contain 0.255 moles of sodium hydroxide? So you have the concentration of sodium hydroxide solution, and you have the amount of solute, the sodium hydroxide. What would be the volume of the solution? Okay, so to calculate this, we can use this as a conversion factor. So we can turn this into a conversion factor. So how do we do that? So these are the numbers that are given. So we're going to turn this concentration of molarity into conversion factor. So we can have 0.125 moles of sodium hydroxide per liter, or 1 liter per 0.125. So now, because we're given 0.55 moles of, wait a second. So this is supposed to be 0.255. Okay, so that's a typo. Okay, so there, I fixed it. So this is 0.255 moles of sodium hydroxide. So we're going to use this information and we're going to multiply it with one of the conversion factors. So I'm going to go ahead and write that down here. We want the moles to be at the bottom so that it will cancel with this moles right here. So we're going to use this conversion factor and multiply it with the 0.255 moles of sodium hydroxide. So now you can see that the moles of sodium hydroxide would cancel each other out. And what you're left with is the volume of the solution in liters. So 0.255 times 1 divided by 0.125 gives us the total volume of the sodium hydroxide solution. So it's asking how many liters of the sodium hydroxide solution contain this amount of the sodium hydroxide. The answer is 2.04 liters sodium hydroxide solution. So you can use this method using the conversion factor, or you can use the formula again that I just showed you earlier. So this is the original formula containing just the moles per liter, right? And so what you can do is isolate the volume by itself, right? So we already have the concentration of molarity, it's 0.125, and we have the amount of solute in moles, which is 0.255. So all you have to do is isolate volume by itself. So we're going to multiply volume on both sides of the equal sign and then divide both sides by molarity. And you can isolate volume using this equation right here. So all you have to do is divide 0.255 moles of solute divided by the given concentration, which is 0.125. And that gives you the same answer. So here's another example. How many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution. So you're given the chemical formula of sucrose. So you have C12H22O11. So this is the chemical formula. And it's asking how many grams of sucrose do you need to make this amount of or concentration of sucrose solution. So there are two ways to do this. The first method is similar to the one I showed you earlier, and then the second method is using the equation or the formula. So the first method is using the conversion factor method. So you're given the concentration of the sucrose solution. So what you can do is you can convert this into a conversion factor. So that would be moles per liter, right? So 0.758 moles per liter sucrose solution, or 1 liter in the numerator and then 0.758 moles at the bottom. And then you're going to use the other information that's given for volume, which is 1.55 liter sucrose solution. So since it's asking for the mass in grams, we can determine the moles of the sucrose solution, sucrose first. And then from moles of sucrose to mass in grams of sucrose. And so using this information right here, volume 1.55 liter sucrose solution, we would multiply this with this conversion factor here, which is shown here on the left, right? Because we want the liter sucrose solution to cancel out, and we want the moles of sucrose to be up top, so that we can convert that to mass in grams using the molar mass of sucrose. So we're going to multiply the two numbers, and you can see how the units canceling out, and you're left with moles of sucrose. So 1.55 times 0.75 gives us the amount of sucrose in moles. So we have 1.17 moles of sucrose, and we have to convert this to grams using the molar mass of sucrose, which is roughly 342.30 grams per mole. Okay, so you can calculate that yourself. You know the molar masses of each element to get the total molar mass of sucrose. So moles of sucrose would cancel out. So now 1.17 times 342.30, and we get about 400 grams of sucrose. So you can use this method, or you can use this formula that I provided earlier. So the concentration is equivalent to mass in grams divided by the molar mass divided by the total volume of the solution. So all you have to do now is use simple algebra to isolate the mass in grams from this equation. So all you have to do is multiply both sides by the volume, and then multiply both sides again by the molar mass to isolate mass in grams by itself. So you would get this equation shown here for mass is the concentration times the volume times the molar mass. So concentration is 0.758 times the volume, which is 1.55, multiplied by 342.3 grams per mole. And that will give you the same value, which is 400 grams of sucrose. So the next concept that I want to talk about here is known as dilution. Solutions are normally stored as concentrated stock solutions. So let's say that you make a purchase for a hydrochloric acid solution, and it arrives in a big bottle, and then on the bottle it'll say 12 molar solution. So that's the highest concentration for acid. And let's say that you perform an experiment and you don't need 12 molar solution, you only need 6 molar solution of the acid. And so what do you have to do? Well, you have to make a dilution. You're going to try to make a less concentrated sample or solution of the hydrochloric acid. And so how do we do that? In order to make solutions of lower concentrations from the stock solutions, more solvent is added. And so in aqueous solutions, our solvent is water. So water is a solvent. In acid, for example, acid solution, the solvent is water. So if you want to make a less concentrated acid, all you have to do is add more water. But now the question is, how much water do we need to add in order to get a specific concentration of that acid? And every time you make a dilution, the amount of solute, the amount of particles in moles doesn't change. The only thing that's changing is the volume of the solution, the total volume. And so you can see how the math works out. So you know that molarity is equivalent to the amount of solute in moles per volume. And so if you're increasing the volume, you're dividing that amount of moles by a larger amount, a larger volume. And so concentration then decreases. And that's how you make a dilution. That's how you decrease the concentration of a specific solution. So let's say that we have a copper solution, and the concentration of copper in that solution is 1 molar. So therefore we have a 1 molar copper solution. Now let's imagine that we take half of that volume, or we're going to transfer half of that volume to a separate container. Okay, whatever that volume is. It could be 1 liter, 5 liters, 10 liters. It doesn't matter. So let's transfer half that volume into a separate container, and then we're going to add equal volume of the solvent, in this case water. What would be the new concentration of the copper solution? Well, that should be pretty simple, because all we did was took half the concentration and then diluted it by adding more solvent, equal amount of solvent. So in that case, we just divided that concentration by half. So now we should have a 0.5 molar copper solution. So how do we calculate the volume of solvent that we need to get a specific concentration of solution? Well, we can use this equation or formula shown here for dilution. And so M1 is the initial concentration times the initial volume, and this is equivalent to the final concentration times the final volume. So M1V1 equals M2V2. So here's an example. Given a 10 molar stock solution of calcium chloride, what volume of the stock solution do you need to make 3 liters of a 0.5 molar calcium chloride solution? So it tells you you have a stock solution, and the concentration is higher, 10 molar. And then it's asking you what volume of the stock solution do you need in order to make this 3 liter 0.5 molar calcium chloride solution. Well, we can use that equation, that dilution formula, M1V1 equals M2V2. But let's write down what's given first. So we have a 0.5 molar calcium chloride, M1, and the volume that we need, the volume that we want is 3 liters. And then we're also given the concentration of the stock solution, which is 10 molar. Now, how much of the 10 molar do we need in order to get this 3 liter 0.5 molar calcium chloride solution? So here's the equation or the formula for dilution. You have M1 times V1 equals M2V2, and we're trying to find V2, right? The volume of the stock solution. So you can use algebra and isolate V2 by itself. So we can divide both sides by M2, and that gets rid of M2 on the right-hand side of the equal sign. And what's left is V2 by itself. So here's the step-by-step process. Now you can see that V2 can be isolated from the equation by dividing both sides by M2, and the M2's cancel out. And what's left is V2 by itself. So all you have to do now is plug in the numbers, right? So M1 is 3 liters times 0.5 divided by M2, which is 10. And plug these numbers into the calculator, and we get 0.150 liter of the stock solution. So you're going to take 150 milliliters of the stock solution, and then you're going to add enough solvent to get a total of 3 liters. So now that you've calculated the amount of the stock solution that you need, you can now prepare the sample, prepare the dilution. So the first thing that you want to do is to add the 150 milliliters or 0.150 liter of the stock solution into a volumetric flask. And then you're going to add enough water all the way to that mark. So assume that this is a 3-liter volumetric flask. You're going to add enough solvent all the way to the 3-liter mark, because according to your calculation, you should have a total of 3 liters of the new calcium chloride solution. So here's a more challenging example here that involves stoichiometry and concentrations or solutions. What volume of the KCl solution or the potassium chloride solution will completely react with the lead nitrate solution according to this balanced chemical reaction equation? So you're given the concentrations of the solutions, including the volume of the lead nitrate, and also a balanced chemical reaction equation. So it's asking you what would be the volume of the potassium chloride solution that will completely react with the lead nitrate solution. So this is a challenging question because you're now unifying multiple concepts, right? You're unifying stoichiometry and solutions or concentrations. So if you remember, stoichiometry is basically defined as the quantitative relationship between the reactants and products. And so your reactants here are the compounds or the chemicals on the left-hand side of the arrow, and then the products are the ones on the right-hand side. So it's asking you how much of the KCl would react completely with the lead nitrate. So you're going to use mole ratio, right, between the KCl and the lead nitrate. So KCl and lead nitrate. And then once you find the amount of moles of the KCl, then you can determine the volume of the KCl solution, because you already have the concentration, right? Remember, the concentration is moles per liter. So you can determine the amount of moles that you need based on this based on stoichiometry, and then from there calculate the amount of volume that you need. So here's a diagram that basically shows you how you would approach a problem like this. So the first thing that you want to do is to determine volume of A, right? And then convert volume of A to the moles of A. And then from moles of A, you can determine the moles of B based on a balanced chemical reaction equation and mole ratio. And then once you've found the moles of B, then you can determine the volume of B using molarity, right? Using the information that you know about molarity. And so you're given the volume of lead nitrate, and you know the concentration of lead nitrate. You can determine the amount of moles of lead nitrate. And then you can use mole ratio between lead nitrate and KCl to determine the moles of KCl. And then from moles of KCl to volume of KCl using the concentration of KCl. So here's the concentration of lead nitrate. We know that the concentration is 0.175 molar lead nitrate solution. It's given right up here. And so this is basically equivalent to 0.175 moles per liter of lead nitrate. So we can determine the amount of moles of lead nitrate by simply multiplying this concentration by the given volume of lead nitrate. Okay, so we're going to multiply this by 0.150, and that tells us, or that gives us, the amount of lead nitrate in moles. So here you can see how the liters, the volume lead nitrate would cancel with this liter of lead nitrate solution. And then you can use dimensional analysis, in fact, to save you some space and time. So now we're going to use the mole ratio between KCl and lead nitrate. In this case, it's 2-to-1 ratio. Right? So we're going to put moles of lead nitrate at the bottom, moles of KCl up top. So you can see how the moles of lead nitrate cancel out. And now we're going to convert moles of KCl to volume of KCl. And for that, we will need the concentration of KCl. Again, this is in molarity, and molarity is moles per liter. And so we're going to put moles down here and then liters up top, because we're trying to get the amount, the volume of KCl. And so we're going to add another train track here, where the moles of KCl would be at the bottom, and then the volume would be up top. So you can see how the moles of KCl would cancel each other out. And then all you have to do now is multiply all the numbers up top. So 0.150 times 0.175 times 2 times 1 divided by 0.150. And that gives us 0.350 liters, 0.350 liter of KCl solution. So this is the volume of KCl that would react completely with 150 milliliters of the lead nitrate solution.